Good morning, everyone. Happy Friday. We'll try that again. I said, good morning, everyone. Happy Friday. Good morning. Thank you to GPSD for allowing us to be here today. Thank you for all of you that are watching on YouTube. My name is Hunter Hardesty. I'm with Gasvoda and Associates, for those of you that don't know me. I've been with the company about 11 and a half years now. I did not start when I was 13 years old. I was 15. So we'll get that question out of the way. I've got two speakers with me today. I've got my friend Sean and Charlie, who will be on after him. Sean is going to be talking about peristaltic pump technology, and Charlie is going to be talking about some big bubble mixing technology. So I appreciate all of you coming in this morning. Thank you for taking some time to be here. And without further ado, I will pass it over. Thank you.
Thank you. Thank you, Hunter. So you even got a clap for that. So I'm Sean Davis. I'm with Albin Pump, which is a part of Ingersoll Rand. I'm already being told I got to move over. So my sales credentials, I've been with Ingersoll Rand since October. I've spent about 22, 23 years in various industries. I've done general industrial, I've done biopharmaceutical, and now wastewater on the municipal side. So our little niche within Ingersoll Rand is Albin is focused on peristaltic pumping technology. You may be familiar with Ingersoll Rand and know for their compressors or other brand names that they have, specifically Milton Roy, LMI, Aero. But again, this is just one of the different pumping technologies that we offer. So Albin was founded in 1928 in Sweden. The manufacturing current headquarters is now in France. We also have U.S. manufacturing just outside Philadelphia in Ivyland. So we know that's a big deal with certain projects that come through, especially anything that needs to be BABA compliant. We can meet that with certain of our products. But as far as myself, engineering background, I cover the entire eastern half of the U.S. There's actually 3 of us working for Albin. We actually all came from a competitor, but we're all ingrained into the pumping technology, and in specific peristaltic pumping technology. So we're going to talk about 2 different types that we offer, our hose pumps and our tube pumps. Our hose pumps you're going to see are more for that high pressure transfer, wastewater treatment, applications that you may have, anything that's got a viscous, abrasive, corrosive, fibrous product going through it. These hose pumps are what you're typically going to look at there. Whereas on our tube pumps, you're typically looking at the water treatment side for those types of applications. Those are a little lower flow, lower pressure, more of a dosing, more precise measurement of any of those chemicals that you're putting into your line. So peristaltic working principle, it's a real easy one. The human body has mastered this with swallowing. That's the same thing, that's peristaltic technology. What we're doing is we're using 2 shoes on our hose pumps, or what we call rollers on our tube pumps. And what those are going to do, they're mounted 180 degrees apart, and they are going to squeeze the hose or the tube that's inside that pump head. And so the compression, the squeezing, that occlusion of the hose is actually going to draw in any of your fluid, any of your material into the pump. And then it gets moved around as those shoes or those rollers continue on throughout the pump head. And then on to just discharge for you. So with the advantage to this, and probably one of the biggest selling points I want to say on this, why is this technology important? Well, 2 of the things we tout on this. One is your only wetted part, the only part that's coming in contact with your fluid is the inside of the hose or the tubing. None of the shoes, none of the pumpage, it's not susceptible to wear because it's not going to be immersed in your fluid. So literally your tube or your hose is the only thing touching your fluid in your processes. What's nice about it is actually a gentle process. Outside of what you see with municipal wastewater, water treatment, this is a big technology for biopharm where you can't lyse the cells. You have to be gentle with them. Olives, fish. I mean, it's all things that have been used in the peristaltic pumping technology world simply because it is a gentle process. Your hose life this is a nice point here too, and something I want everyone to know, is your hose life is mainly determined by the number of squeezes of the tubing, not by the abrasiveness or the fibrous nature of your material or your fluid going through that. So based on the number of squeezes, that's where you're going to be looking to do your hose changes or your tubing changes, not based on the material that you have inside. So we have different types of, bless you, we have different types of hose and different types of tubing that are meant to work to be chemically compatible with any of those chemicals that you may be using as well. So it's a variety of hoses or tubing that we do offer.
By a show of hands, anyone use peristaltic pumps now or familiar with them? Okay, cool.
So I like that. That's good. So we already talked about how it's the one wear part. It's that hose that you have. The advantage to this is the pump can be repaired or maintained in place. We actually, there are some alternative brands that you actually have to send in the pump to get it maintained or get it fixed. Here, you're able to replace that hose on site, in site. You don't have to move it. You just want to ensure that there's a minimal distance, and I'll show that later, a minimal distance for being able to put that hose in or take the hose out from your pump. But an advantage to peristaltic technology is that the pump orientation or port orientation is any one of 90 degrees. So it's meant to be able to be put in place where you have the space. You don't have to create the space for it. We offer different port orientations to allow for ease of operation, ease of maintenance, and ease of putting it in site or on site. What you see with peristaltic technology, it is truly a positive displacement pump. It means you are moving 100% of the fluid through. You can recover all of that fluid as well. If you ever have a blockage or ever have an issue, it can actually be reversed in place. There's nothing special needed for that, so you can actually clear the line. You can remove any of that fluid that you have in that pump head, so you are truly getting 100% flow or fluid movement on that. So it's also can run dry, which not a lot of the other pumping technologies can, and you will not suffer vapor lock because it can move those gases through the line as well. So a couple advantages to the peristaltic technology there. So I've already mentioned a few of these things here. No wasted product, no seals to leak or to wear out on these pumps. What's nice is that, again, we talked about some of that bigger material. You can have up to 65% solids that can be pumped and material that's up to 25% of the internal diameter of the hose. So there's a wide variety of sizes of these hose pumps. So if you did have something large or had one of those applications where, you know, you're getting a lot of fibrous material through or just a lot of junk, a lot of sludge coming through, these are able to handle that without difficulty. With putting peristaltic pumps in place, you could get up to 31 feet of head vertically. Horizontal distance isn't as much of a consideration, but one of the best practices for peristaltic technology is you want to get it as close to your application as possible. It is more of a consideration when we're talking vertical distance, not necessarily horizontal distance. It will pump what you need horizontally. So you see in a picture here, this one actually has 3 rollers. What we have, we offer some 3-roller peristaltic pumping, peristaltic pumps, but we find 2 shoes or 2 rollers inside is going to be a best practice here. The simple reason for that is the more rollers you put in, the more squeezes you're going to have, and then you're going to wear your tube life faster. And again, that's what we're trying to avoid. Claim to fame for peristaltic technology is that it's going to be operator efficient, operator friendly, maintenance friendly, and low maintenance time to simply change out the hose or just change out that tubing for you. So what you want to do is a majority of our pumps and a majority of the pumps that are out there that are peristaltic technology utilize the 2 shoes or 2 rollers so that they can put through as much fluid as possible for that size pump, as well as not to squeeze the tubing or the hose more than is necessary.
Any questions so far? Everything makes sense? Cool.
We talked about some of the things here. I had previously mentioned the minimum distance for actually changing that hose, because some of these hoses can be quite large, but they will set through automatically into the hose pump. And we'll actually have a video of that, so you can see just how easy the maintenance is on this compared to some of the other technologies that are out there for pumping. If you do ever come across or have a highly viscous material, one of the best practices we recommend increasing the size of your hose or running slower. The name of the game with Peristaltic technology is low and slow. You want to run it as low as possible, as slow as possible, simply because, again, it all comes back to the number of squeezes, the number of occlusions, the number of closures of that hose, and we want that to last as long as possible for you. So some of the advantages that you'll see here versus some of the other technologies is literally your only wear part, we've just talked about this, is going to be the hose, whereas you have a lot more parts that you have to worry about maintaining on, say, progressive cavity pumps, the stator wearing out, burnout. It's literally just the hose that's being changed on here. And what I'll show you is, got a list of what the maintenance is on the hose pumps, and really it's just visual inspection. Okay, you're going to change the hose, but you're going to just inspect the other parts visually. They're good, and then you can move on. It literally is majority of your time just going to be changing that hose. Another piece of ancillary equipment that's not needed versus a progressive cavity pump is going to be the pressure sensor and the stator temperature, because if that is not have fluid in it, it's going to burn out, it's going to wear out, you're going to have to change it. There's a lot more parts that need to be changed on that versus just a hose or a tube for peristaltic pump technology. Similar again here, more ancillary equipment that's not needed on peristaltic pumps that you're going to find on our competitive technologies. In this case, it's the mechanical seals, and those aren't necessary for peristaltic technology. Remember, the squeezes or this closure, the shoes closing or the rollers closing, your tube or your hose is acting as that check valve as well. So there are no temperature or pressure fluctuations, anything you need to worry about having ancillary valves to make sure that that is not something that's going to be a problem in your line. And just mentioned it here, the discharge check valves. That's not necessary on peristaltic technology because your tubing technology is actually, or your hose technology is actually acting as that check valve for you. Rotary lobe pumps, this is another competitive technology here, and what we're just showing you here is the number of parts that are needed for rotary lobe technology pumps versus, again, the only part you're maintaining is going to be that hose on the peristaltic hose pump. We mentioned this earlier, that the different port orientations, this is going to allow ease of operation, ease of installation, ease of maintenance, so that you're able to set it easily in place where the pump is needed. So what you see here is a wastewater treatment plant lime milk application, which showcases the fact that we have different configurations for the gearbox as well. So if you're space limited, peristaltic hose pumps can be arranged in such a way to make them more vertical rather than more horizontal with that gearbox. So you got the right angle reducer on there as well. So another one of the capabilities that peristaltic hose technology offers. The one thing I want to mention on this slide right here is the ability to have multiple hose pump sizes available. Because again, what you want to do is you want to run low and slow. But in that case, if you have a higher flow application, some of the competitors, they offer duplex systems. Well, that's just adding more floor space. That's just adding more metal that you're paying for in the pump housing itself. So if you're able to take care of that with just one pump rather than having duplex system, it's typically going to behoove, or it's going to be better for operators. And again, just to see that these go all the way up to, we have hose pump technology is able to get up to about 220 psi. These are your higher flow, your higher pressure applications. We'll talk about tube pumps, more dosing, more metering in a bit. But you could see you could get up to 660 gallons per minute on this, which is 22 gallons per revolution on that pump on the right, the largest hose pump that's offered out there. It's massive. It's bigger than me. Some of the recommended accessories we state for this technology is going to be your leak detector. On tube pumps, it's inherent, already included in there. On the hose pumps, it is an accessory after the fact. But this way to just ensure that you're forewarned, or there's a trigger or alarm triggered if for whatever reason that there is a leak in the system. And unfortunately, we do see it simply because we forget to check on the pump. We forget to see when it's actually going to have a hose bump, a hose burst, or a tube burst, when it's just run too long. This way, you can be warned about it if there is any leak detected in that. One of the things to kind of pair with that is our revolution counter, which is going to offer you predictive maintenance. You're able to run the hose, your first hose, to failure. And then you can dial that back by about 90% is what we recommend. So if your hose burst at 5 million revolutions, you dial it back to 4.5 million revolutions, and that'll give you the predictive failure mode. So you won't have that leak, or you won't come close to that leak. So paired with the leak detector, it's just a way to protect your process. Again, some other accessories here that are offered if necessary, but there's custom configurations on Peristaltic hose pump technology. One of the things that's up here, ATEX consideration, certification, custom skids, trolleys, anything like that that's just going to make it easy for you, but that's all stuff that can be built in. We can even put these large hose systems into skids as well, built-in custom skids for you if that's necessary. Again, we keep going back to the hose. I keep going back to the hose, but that's going to be the heart of the pump. What a lot of I want people to understand is this is where you're going to get your performance. This is where you're going to get your expectation of what you need your process to do. It's going to be the hose. It's going to be the tube. It is not just a commodity product. It is going to be the driver for you getting what you are expecting out of your Peristaltic hose technology. It's the most important part of the pump. What are some of the considerations for hoses or for tubing? One is going to be chemical compatibility. As you see here, just in this picture, it shows a variety of different materials to ensure that it is chemically compatible with whatever application that you have. Something that's nice too, in not just on ours, I'm saying, but easily identifiable by the color, custom color stripe on it. But again, these are made to be, your durometer, your hardness is what's going to judge this performance, because why is that important? Well, that's going to determine your restitution or your bounce back for the hose. If it's too hard, it's not going to bounce back enough, and then you're not getting that full internal diameter of flow going through, or your product going through that ID when it's still closed and not restituting. Then you can have blockages. So this is why I'm saying the hose, the tube, is going to be the driver for your process. One of the things you always want to consider is going to be warranties. There's 2-year warranties offered. There's 5-year warranties. There's warranties on the gearbox. But this is important to note too, because not every company is going to be the same. What you will find though that is not covered are going to be your hoses, ball bearings, wear rings, any of that stuff that may wear. But again, on the gearbox, on the pump itself, your warranty considerations is something you want to take a look at there, because not all competitive type technologies are offering that type of that full warranty on it. Do you want to play this video, or am I able to play it? Oh, wait, I went back. How do I play it on this?
I think you just click like you're going to move to the next slide.
Yeah. Okay, it's not playing for me on this.
Yeah, it's different.
Okay. Yeah. Sorry about that. There you go. Thank you, I appreciate it.
Allow enough maintenance space between the pump connections and the wall or any other equipment. The maintenance space is the minimum required distance for an easy hose replacement that depends on the pump size. The hose is the only wearing part of the pump. When pumping critical products, for example, expensive or aggressive substances, it is recommended to install a leak detector for an added level of protection and to stop the pump should a leak be detected. Albin Pump offers a complete range of pressure switches or capacitive sensors for the complete range of the ALH series. Combined with the optional revolution counter, preventive maintenance of the hose is possible. To begin the hose replacement maintenance process, the suction and discharge piping must be disconnected and removed. The lubricant must be drained from the pump casing using a draining tool. At the suction side, loosen the hose sleeve and hose insert clamps to extract the insert and flange. Proceed to the same action at the discharge side and remove the flange brackets. Run the motor at jog speed to remove the hose from the pump casing. If necessary, remove the pump cover and clean the pump casing to remove any residue of lubricant or hose. Reassemble the pump cover.
So what's good about this, if you don't have a leak and you're just preventative maintenance, you're changing the hose, you can actually reuse that lubricant.
Coated with lubricant.
We say to change the lubricant every 5,000 hours of use.
Assemble the flange on the flange brackets and insert the hose by the discharge port. Reverse the direction of rotation and run the motor at jog speed. The shoes will compress the hose and will push it to the suction side. The insert must be assembled and the clamps tightened to ensure the correct position of the connection assembly. For the assembly process, refer to our manual to check the correct tightening torque to apply. Proceed to the same actions at the discharge side.
So what they're going to talk about coming up here are shims, or shimming the hose. Any company is going to give you the recommended number of shims to put in, but it plays a vital role in properly squeezing or closing the hose.
Which considerably reduces the hose lifetime. The number of shims depends on the pump size, the speed, and the back pressure. Refer to the Albin shimming table to set up the right number of shims and get the maximum performance of your pump. Since 1928, Albin Pump has manufactured peristaltic pumps for numerous industries. The ALH series will continue to earn your trust for years to come.
Okay, beautiful. So the slide I have up in here, but I could just briefly move on from this one. We do offer clean in place availability with our pumps. It's on 4 standard models, but this is something you're going to find more in biopharm, cosmetics, some food and beverage, but I don't see it as much in municipal, but it is something that is available as a part of the technology, as a part of peristaltic pumping technology. The shoes actually will backtrack or will rotate so that they're out of the way, so that you can clean the inside of the hose in place. So it's just something that this technology also allows. So as I stated, there's about 14, I believe, steps here of what you would typically look at in maintenance, and only one of them is going to be the predictive maintenance, and that's going to be the pump hose replacement or the preventative maintenance. The rest of these, you're just checking when you do your hose change or when you have the line down, looking for any type of wear, any type of discoloration, any type of leak. But again, the main thing that you're going to be doing to maintain these pumps is going to be simply that hose replacement. Different applications that we see, these are the most popular applications we see on the wastewater side. But any type of sludge, any type of aggressive, corrosive, tougher, abrasive material is where we're going to be typically considering the hose pumps versus our tube pumps.
So this is where I was going to ask what you guys were using your peristaltic pumps for currently. There was a lot of different ways you could use them there. Are you guys using them more for like dosing, for smaller pumps? Do you guys use them for moving sludge? A little bit of everything? What's your guys' past experience?
Mm-hmm. Okay. Well, yeah. Mm-hmm. Yeah, so you'll see some of the applications here. These are designed, peristaltic hose pumps are designed to be either inside or outside. They're fine for aggressive environments. There's a wide temperature range that they're able to be subjected to. But you'll see the different setups that we have seen here. Although, I'll point out, this is something you typically want to avoid. One of the best practices for peristaltic hose pumps is you don't want to have a bend, especially a bend coming right out of the pump itself. You want to make your bends as big as possible in the piping. We also typically recommend that in best practices you use a flexible pipe or flexible hose coming out to help dampen any type of pulsation. You don't get a lot of pulsation with the peristaltic pumps versus say like a diaphragm pump. But again, these are just some of the best practices we've come out with since not just us, but anyone doing the peristaltic technology has been a part of. So this is the one I was showing that does the 22 gallons per revolution, just how sizable it is. So, but again, we can do custom skids, inside-outside placement, trolleys, anything to help. Peristaltic technology, people are going to manufacture those and make them available as accessories. So now switching gears a little bit more to the dosing and metering side. I mean, it's really the same, just smaller package. Lower flows than hose pumps, more accurate, higher turn down, which I'll touch on in a second here. But these are going to be your more of your dosing, your water treatment applications here. And you're just seeing two different types of the peristaltic tube pumps that I know that we offer, but similar to what you're going to find from others doing peristaltic technology as well for the metering pumps. Again, you're seeing the same thing as you saw. In this case, it's going to be rollers. It's more of a gentle compression than it is with the shoes on the hose pump, because obviously the hose is going to be a lot stiffer. It's going to require more force. On these, and it's just going to be your tubing, you don't need as much of a force, so we go with the rollers here, even more gentle than the shoes. Now, it may look like we have 4 rollers in there, but only 2 are compressing them. So you'll see that in peristaltic technology. It's just those are guide rollers, the ones that aren't actually closing the hose. So I didn't want anyone to think I was lying to them about using only 2 before, and now we're showing something with 4. That's not the case here. So so all the stuff I've talked about before, I don't need to rehash this in just the best interest of time. But the most important things are down here. The lowest total cost of ownership, simply because all you're doing is you're changing that tubing element in this. So your wear part, again, same thing for the peristaltic tube pumps. Then the peristaltic hose pumps is your tubing is going to be your only wear part. One of the things that makes life easier is just having a nice HMI. You'll see these on peristaltic tube pumps, but you want to have something that's easily readable, easily identifiable, and hopefully protected. So if there's any corrosive fluid or material that gets on it, it's not ruining your HMI. But again, something with a nice, easily read, easily identifiable stages and steps and what you see here. This we'll go over in just a bit. But what's important on something like this, we have another advantage to peristaltic tubing technology and peristaltic tube pumps. That's operator safety. Okay, so this is something you want to consider. Not all pumps are going to be made the same. You know, the technology is similar, but not all pumps are going to be made the same. There are some peristaltic tube pumps out there. It's a 24-step process. The rotor's actually moving while you're changing the hose, and you can break a finger. And I'm going to show you warnings up there. So what you want to consider, want to look at, is going to be the operator safety aspect of it, keeping your hands away from the rotor, and the rotor being actually stopped when you go ahead and change that tubing, which I'll show here in a moment. Again, an advantage, we're getting rid of a lot of ancillary equipment versus competitive pumping technologies. As you see on a skid, a custom-made skid or a ready-made skid that's available for the peristaltic tube pump versus what you're going to find for a diaphragm pump skid. And these are all the ancillary objects that you will not need. You will not need to maintain, not need to worry about, not need to buy, because it's not necessary for peristaltic tubing technology. So with diaphragm pumps, that's going to be more of a competitive technology to peristaltic tubing. What you're going to find is the fluid remains in the tube, so it's less parts that you have to maintain. That's the claim to peristaltic technology. You've heard me repeat it quite a few times, but that's the important thing to note here. Much better at moving the abrasive, the aggressive, the viscous material as well versus a diaphragm pump. Again, no seals, it's self-priming, all just advantages to using that technology versus a lot of people are familiar with using diaphragm pumps. And, you know, again, the ancillary equipment, there's a lot more vibration, there's a lot more noise. On even our hose pumps, the larger hose pumps, you want something that's not going to be harmful to your ears. So I know just in our case, the noise level doesn't get above 60 decibels, which is office conversation. Unless your office is really loud, I don't know. There's a different type of peristaltic technology that is relatively new, and one that if you use the dosing pumps, you may have seen this before. I'm not going to name any names up here, but it's what we call a cartridge head. And so the lubricant, the tubing, the rotor, everything is set inside the cartridge, and that entire cartridge gets replaced. It's still peristaltic technology, but now everything's self-contained within the cartridge. Well, it's different in terms of that entire cartridge needs to be replaced. And there's no bleeding your fluid out of that cartridge. There is a valve there, but it's only for pressurization, and that's it. There's no way of getting your fluid out. If you have a leak, you have your material in there, you have your lubricant in there, where's it going? It's going to landfill. It's not very sustainable. Whereas with peristaltic tubing technology, that is not the cartridge head, you can completely drain the liquid out of the tubing, and you're just throwing away a much smaller part. And the cartridge head's about 10 times more in cost than just the tubing element. Just going to say that. So it's simple, not a lot of parts. As you saw, a breakdown of some of the progressive cavity pumps before. I don't know if I did show one of the diaphragm pump, but this just goes to show you what goes into the pump head in the tubing element, and it's just that easy. So the reason you'll see a dual, there's single or there's dual tubing elements out there. Well, the advantage to dual is you're doubling your flow with keeping it in the same pump head, same size pump itself. So again, if you're doubling your flow capabilities, you're not having to squeeze as much. You're extending the life of your tubing. And again, much better total cost of ownership. There's just a lot of different accessories, considerations, things that you may want to keep in mind. What's your communication? Sealed versus unsealed. Is it serviceable on site, or do you actually have to send it in? Yes, there are some tube pumps that you have to send in to be serviced, and I mean that just kind of defeats the purpose of ease for the operators. One thing I want to say though is turn down as well on hose pumps. That's another thing. you're looking at like a 50 to 1 turn down, 10 to 1 turn down. On the pumps for municipal, for peristaltic tube technology, you're looking 10,000 to 1. It gives you a wide range of flows that you're able to accommodate. And it gives you that precise dosing because you are getting the same amount of fluid with every rotation of that rotor, of that pump head. And so it's very predictable. But also, again, wide range, higher limit and down to a lower limit of what you can achieve for your flows. Doesn't want to. So again, this is similar in the fact of it's just routine maintenance. You're changing out your tubing, but you're just doing a visual inspection. Does everything look good? Are there been any leaks, any discoloration? But a majority of your time, you're just changing out the tubing element. So one of the technologies you'll see, I talked about operator safety. First of all, having the maintenance manual on a pump is going to behoove you. You know, who wants to carry the maintenance manual around, and most likely it's going to get lost. So now you have everything self-contained within the pump itself. What's nice about this is it takes you through all the steps. It's also going to keep your hands away from when the rotor does move. You'll see what I'm talking about here in a moment. But then the rotor is not moving at all when you actually physically put the tube element in, so it is now safer for you. No. Yeah, let's do this one. So this will show you an example of what I was talking about. I'm sorry, I just went back to it, so I need to get it to play again. I don't know what you did. I'm sorry. Thank you. Sorry about that. So what it's showing you is you're putting your fingers up at top. You have to engage both of your hands so it's not by the moving rotor. I'm almost done. Almost done.
So for those of you that have had to replace one of these and have had to put your finger in the way of the rotor, you can break a finger. Seen some gnarly things happen, believe it or not. So the fact that it is not moving during that is pretty beneficial, if you ask me.
Yeah. So this is the example I told you. This is taken directly out of a different manual. There's the safety warnings in there. Some of the changeouts, you need to utilize a tube changeout tool, which can easily get lost. So again, one of the considerations when choosing which particular type of peristaltic technology you want to use, these are all things you want to think about because again, this is how you're going to be spending your time after the pump is in. It's just really replacing the tubing itself. This is just an example to show it doesn't matter what you're pumping, what your application is. There's tubing that's manufactured for it. Whether it's more of an aggressive chemical and needs a reinforced tubing, or if you're operating in the presence of fats, oils, and greases in more of a petrochem type of tubing element. But manufacturers are going to make it so that there are options available to you depending on what your actual application is. Similar, I briefly mentioned it with the hose pumps, but one of the availabilities for you is Peristaltic technology. Fits nicely in standard and customized skids for you, whether there's simplex, duplex, triplex, even quadruplex, which is one of the recent ones I just did. But custom configurations available for you, standard configurations available for you, but all self-contained, all small footprint, so that's not taking up valuable space. And again, some of the applications we're seeing the most in what we do on the municipal side, but all of, just speaking on our side of things, these are what we're going to spend most of our time on and see that peristaltic technology is best for. And I think that's it. Just sat down.
Thank you, Sean. If you guys have any questions, comments, horror stories you want to talk about, feel free. If not, we'll take a little break before we get started with the second presentation. Nicely done.
Thanks. And thank you all for your time and attention to that.
Shut this off. literature. We got. I'll pick it up and stuff.
We can put a table. You want to put it on the table real quick?
Yeah, sure. Yeah, I'll pass those around. Yeah. Maybe just put it off to the side there so I can walk around in front, maybe.
Let me see if I can even.
I mean, it's not a big deal either way.
Yeah, just when he goes over, I'll just move the camera. We'll be okay.
Drink of water.
No, that little guy there does work. So if you wanted to put it in your fish tank out there, it's far more impressive when it's a lot bigger though.
All right, everybody. I'm going to get started with the second presentation here. We're going to switch it up a little bit. This is going to be on some big bubble mixing. Going to introduce my friend Charlie here. He's from Milwaukee, but we still like him, so that's okay. He might have a little funny accent, so just give him a break, okay? In all serious, though, Charles is a very smart guy. Very interesting technology. I think you guys will like the low pressure aspect of it. You guys probably have seen something similar with a high pressure system. So I'll let him do his thing. Charlie?
Thanks, Hunter. Good morning. Is it on? Yeah, good. Yeah, my name's Charles. Our company's called ENG Designs. Our flagship product then is the Hydrabubble. Am I on camera? Fine.
Yep.
Okay. Yeah, let's get started. So, two of us in the company. We started about 9 years ago now. My partner Brian, he now lives down in Florida, luckily, and he's master's in engineering. He's a hydraulics pneumatics expert, does Wizard and CAD, and so we do all these designs ourselves. My background is more in civil engineering. Went to Wisconsin and then ended up going over to Norway to do a master's degree there, and then worked several years in Oslo for a company called Aqua Team, basically doing R&D work. I did a lot of piloting. They would send me around all over Europe just because things tended to work when I was around. So got to tinker with a lot of different technologies, a lot of process, a lot of things like that. And then together we started this in roughly 2017, 2018. I started in my garage, basically making these things out of PVC, tubing with a ready heater to bend things, and epoxy, and it was a mess. But things have come a long way since then. So our product is a large bubble. I mean, the units themselves are here. This is a working unit. We would install this right now. Basically, you can think of it as an extreme coarse bubble mixer. So we're making a very, very large bubble, which creates a lot of upward moving flow, essentially. So it's very efficient in terms of actual water movement. So compared to just a coarse bubble mixer, where you're just blasting air through, perf pipe, this collects air under the water and sends it up all at once. So the movement of the water is, we need about 10 times less air to do the same amount of movement that, say, a coarse bubble aeration system would do. Compared to high pressure systems, you may be familiar with a couple of them, where they're just injecting compressed air into the water. Simply because we're not using all that compression energy, it tends to be more efficient than even those efficient systems. Now, as far as maintenance goes, we have virtually no maintenance. We have no scheduled maintenance whatsoever on these. You put them in, if you give them air, they will make large bubbles. As far as wear parts go, we do use some diffusers that have roughly a 10-year life. Anything else is just piping, and everything else is above water. So blowers and things like that, obviously those need maintenance, but as far as in-water parts, it's relatively maintenance-free. As far as capital and operational costs go, we tend to see our systems for, say, B&R conversion or something like that, are very, very cost effective on the front end, and then operational costs are very low just because we're using, it can be just waste air, plant air that you're already using for your aeration. So very cost effective that way. So here's just a couple of videos. These are taken several years apart. The one on the right's the older one. We've played around a little bit with just orientations and orifice sizes and things like that. What this is, the video, or both of these are running off a 1/2 horsepower, just a radial vane pump. So just a little guy like this, full bore on, and it's going down to, the bottom of this pool is 12 feet. So we have these units mounted down at the bottom of the pool. Just running an air hose down to them. They're affixed to a giant slab of concrete. Needs to be about 200 pounds to hold these down when they're full. Basically all that's happening here is we're just filling with air, and then it'll collect, and then shoot out a bubble. And you can see from the wall there to the lane line on the right side there is about 18 feet. Just gives you a sense of scale. And this isn't a swimming pool here, so gutters are designed to hold wake, right? You dive into a pool, gutters take all that wake. So if you do have a sidewall, a lot of that energy isn't dissipated out towards the gutters. So you get these currents that end up forming.
The reason I like that video also is it shows the violence and the turbulence of the bubble when it comes up. This isn't a very clean swimming pool, obviously. If you put this in a digester or a dirty application, you can imagine the amount of turbulence you're going to bring up with you with that large bubble. Charlie's going to get towards it, but it's essentially an upside-down toilet, as if you could imagine that's how it's going to work. I'll let him keep doing his thing, but I just like that video because it shows how violent that bubble truly is coming out.
Let me see, how did you get the video to play again?
I told you he's from Milwaukee, see?
This one, so go back and then forward. There. Okay. So anyway, yeah, one thing I didn't mention here, you see these particles that are floating down in front of the video screen there. These were placed in a clean pool. So this was, this pool is filtered. It's literally grabbing stuff off the bottom and resuspending that in a clean pool. And we were actually, mounted about this far off the bottom as well. So, when you add these to, say, a wastewater application, say in an anoxic zone or something like that, you're really moving stuff very effectively around. So how this works, I don't have the internals on here to show you, but basically this unit takes air, it bubbles up inside of there. So you can think of it as sort of like an aeration grid. So passively collecting air, so we set these on top. Air fills down until it reaches a critical point, and then once that happens, the air, basically, there's one path outwards, and as soon as that air goes out, creates sort of a low pressure zone. Bubble starts going out, water then rushes in and pushes the rest of that air out all at once. Okay, so That bubble's then released, it sort of coalesces, and then is displacing a lot of water as it rises very quickly. The speed of a bubble rise is based on basically the diameter of that bubble. So the larger the bubble, the faster it's going to move through the water. There is, obvious terminal velocities on that, but for this bubble, for this size of a unit here, we'll be rising at about 4 feet per second. So a bubble will then coalesce, sort of turn into an amorphic mushroom, and then pushing water out of the way, and then that sort of induces a vacuum up behind it. So then it's pulling water right from the bottom of the tank up to the top. Once that bubble reaches the surface, once that breaches, all that energy, the upflow, has nowhere else to go but outwards. So then it flows out radially from the center of that bubble until it hits something else, like say another bubble's wake or a wall. And then basically what you're doing is generating vertical convection currents in the water. So this is very difficult to do a CFD model for an amorphic large bubble. But basically you're inducing a flow field from the bottom of the tank, pushing that up towards the surface in sort of a plume, and then the water then will return back down to the bottom of the tank, and you form these vertical convection currents in the water.
I'm going to pass this mini unit around again. Now Charlie's kind of explained how this works and might make more sense. I probably should have waited at the beginning. Sorry about that.
What was I going to say right there? So you induce those convection currents, and it's very effective mixing. Other large bubble systems will do essentially the same thing. Depending on the bubble sizes, other systems have multiple units in an array. Others use just another large amount of compressed air at once. But all large bubbles kind of work in the same, almost the exact same fashion. It's just the formation of the bubble and how that's done. The bubble doesn't really care. It's doing the same work no matter how that's formed. Different applications. We've had most of our luck in anoxic sort of selector zones, conversions from an aerated, coarse bubble aerated tankage to anoxic zones using the large bubble, selectors, things like that. We can do anaerobic. There's virtually no transfer of oxygen with the large bubbles. It's rising through the water so quickly, and relative surface area is very small. So Henry's law, you don't have the diffusion into the water, whereas with fine bubbles, you want really tiny bubbles that stay in the water as long as possible to get that transfer of oxygen to the bulk water. The large bubbles don't do that. There's just not enough time, and the bubble's relatively small in that surface area just because it's like a giant blob. Where else? So attractive applications for this would be, say, like extended aeration. So you can combine this with, say, a fine bubble aeration system and use the large bubble for the motive force of moving stuff around in the tank, and using the fine bubble as your efficient means of adding oxygen to that tank. Fermentation basins are interesting. So if you're running a BNR process, for example, you can put your air supply on, say, a valve, turn that on and off as needed. So you could run a sludge blanket for a few hours, allow VFA formation, and then turn the bubbles back on, and they'll start to mix everything back up, move it along, and just run that in a cycle. Channel mixing is very attractive, where if you have, say, just a long straight row of channel, you're using coarse bubble aeration right now, just burning through electricity with all that air that you're adding to it. Large bubbles will give you that motive force. You're using about 10% of the energy that you would be for that, and often there's an air header running along that line anyway, so you can just tap off of that and put these in. We do have a way to ballast these units, so we can put them on, say, either a steel plate, or I'll show you in a second, where we drop them down in situ. Obviously, you want to know what's at the bottom of the tank, but you can drop them down without emptying the tank, and you'll have that mixing. So supplemental mixing applications, things like that. As far as something like a lagoon, we do like to have the amount of energy they're putting in the water is a lot dependent on the depth. So with a very large bubble, if you have only, say, 5-6 feet, we want to use a smaller unit in order to disperse the mixing energy around in a large area, just more dispersed in that. Sludge storage tanks. I don't know what the upper limit of solids concentration is. I'm perfectly comfortable at 3%. I believe we can go up to 6%. It'll depend a lot on the viscosity of that. You can think of a large bubble like, if you take a straw and a cup of water and blow air down to the bottom, you see those bubbles rise really, really quickly. But if you do that with a milkshake, it'll come up in a bloop. With viscosity, bubbles are held together a little bit more. So as far as sludge, like heavier sludge, your mixing diameter isn't going to be as large as, say, in an activated sludge application. EQ tanks are interesting because what happens with this, if you have a continuous flow of air going to these, and like I said, we need some depth, but we also can change the intensity, so the amount of bubbles per minute, for example. If, say, the water level lowers, since we're using low pressure, the compression of that air isn't as much. So it'll automatically increase the rate of bubbles when that tank level goes down. So when you have a greater depth, you get more efficient mixing that way. But then with that lower depth, if you're running the same amount of air, that same pressure, it'll just increase that rate. We do not have yet NSF certification, but we plan to be doing that relatively soon. So for potable water applications, things of that nature, water towers, standpipes, things like that. One thing I will mention now is with these units, what we can do, if you've seen those little ones that I was passing around, we have an air line run to them, but we can also run, say, a dosing line with a peristaltic pump, for example, running these right into the unit. So every time that bubble bursts, you can dose chemical right into it. That's entrained into that bubble, dispersing into the bulk fluid very, very rapidly, which allows you then to potentially use less chemical because you'll have detection sooner. You'll see that disperse more evenly in a tank. So for like pack or pass, or if you're doing carbon addition or something like that, chemical additions, things of that nature. Okay, so right now we manufacture 3 different sizes. This is our flagship. This is our 1.5 cubic foot unit. Our 0.75 is, so this is about 11 gallons. So each bubble is 11 gallons. So imagine holding down 11 gallons of, milk gallons underneath the water. You get a lot of force. You can't do it because this will hold up about 200 pounds of concrete. Smaller units, if we have a shallower tank, cut off roughly about 10 feet. If we have a shallower tank, we'll disperse them more frequently throughout a basin using the same amount of air. You just have more bubbles in different areas. The smallest units, we still a large bubble, 3.5 gallons or so. Those are specially designed to fit down like 16-inch manways. So if you had an HDPE tank or something like that where you wouldn't have access to put something this large into, we can put those units in there. And that's generally the specific application we'd use those for, but they are available. Installation is super easy. Essentially, we're just bolting this down to the floor or to a ballasted piece. I think the next slide will show that even better. So this one I might have trouble starting because this won't go. Oh, there you go. So essentially that's the installation. We'll put chemical anchors in when we're mounting to the floor. Chemical anchors, you just bolt it down. And then we run an air line to that with the diffuser. And the diffuser is for, I'll talk about that in a second. So we are completely agnostic to the type of tubing or pipe that's used. Can be stainless, can be PVC. We like to use PVC a lot simply because it is low pressure, and then the installation is very, very simple. But if the plant requires stainless or something like that, we don't care. It doesn't really matter. You just make sure air's going to it, and it'll make the large bubbles. And it's designed to be very, very simple, so not a lot there. So when we're running an array or a zone, essentially what we're doing, we'll run a single header down and then branch off. So the diffusers that you see there, we just use sort of a snap cap diffuser. That's to give a little bit of back pressure in order to evenly distribute the air to each one of the units. So we'll run a main header down and then branch off to each one of the units. So if you had a zone, a tank, each one would have its own header, and then that would be your control there. So you can do an adjustment with the valve, turn things on and off, and you turn your whole zone off just from that single. They can be piped individually, but this is a lot simpler to install this way.
Does that make sense to everybody? There's really not a whole lot to it. It's very, very simple. That's kind of the whole point of doing this, is just making it very easy, not a lot of moving parts, very low maintenance, still gets the mixing done with a lot less pressure. Just want to make sure everyone kind of understands it's very simple.
So as far as installs go, this is kind of what it'll look like. These are some smaller tanks. These are industrial tanks here, which is by the round. But you can see how simple this installation is. So most of the brains of the operation are going to be outside of the tank with your blower, VFD, or whatever valving that you might want to use for controls. But we'll always design in cleanouts for the piping itself, and then as far as that goes, the diffuser head there is your cleanout for the branch piping. And so if there was any maintenance to do with these units, all you'd have to do is unbolt them, or just take off the nuts, lift up the unit, and then do whatever you have to do. But there's no planned maintenance on these whatsoever. So just in different configurations. So like I was saying, so for channel mixing, for example, so if you had a main header running out along the tank, you can just tap off of that on each one of them. We can run that piping down at the bottom, doesn't really matter. The 75-foot diameter just kind of gives you an idea of how many units you'd need. I think this was for some sort of sludge application down in Georgia. Baffled serpentines, so bubbles aren't magic, they're not going to go around walls, so strategic placement is important. For us to design something, all we'd need is dimensions of the tank, your depth, your width, length, and then what you're trying to do in there. Gives us a really good idea, and that allows us to design that for you. A sense of scale here, so each one of those tanks on the bottom right there would be 20 by 40. So 4 units in that would do adequate mixing for, say, mixed liquor. We call this hydrofusion. This specifically was a sludge tank. What we're doing here is adding aeration and having the mixing. We're using the same blower to do that. Basically we're just adding enough air to keep things from going septic, because the bubbles do not aerate very well at all. And so we can add those without being septic. The reason these are at different elevations like this and around in a circle is when you're controlling low pressure flow, you want to keep things on the same plane. So we can run these different elevations, but if we had the main header piping at different elevations, you would see one fill up a lot faster than the other one. I mean, it's just like an aeration grid. So we just keep everything for slope bottom tank, for example, at different elevations like that. This is an example of extended aeration. So basically an aerobic digester. One blower on a VFD will run all these units. So you get the mixing from the large bubble, you get the aeration, and it's just a continuous operation. So some more videos here. So this was actually very, very early. This was taken in Waukesha, Wisconsin. The first iteration of our units here. In I think 2018, 2018. So 18 feet of depth, they let us put this in the clarifier. I had just this little tiny pump. It was about, I think 125 watt, so 1.6 horsepower little pump, rocking piston. So it only could fill this thing up every, I don't know, a little over a minute per bubble. But you can see the power of that bubble that's, as it hits the surface. And it's a little faded on the screen right now, but you can see that plume of sludge coming right up off the bottom of the tank. So in a tank of this size, for example, you'd need quite a few more units, but you'd also up the intensity of this. And you can see how that's going to continuously mix and well mix a tank of this size. As far as ballasting goes, we've been playing around with different configurations. Concrete's cheap, so we can mount those to the sides there. Turns out that's a little bit cumbersome. 350-pound weights of concrete. What we're doing now is, if we are adding these to as a ballasted thing, drop in situ, we'll take a steel plate, powder coat that, weld points on there, and drop that down into the water that way. But installation super simple. So this is Jason. We're up at a plant in Belmont, Wisconsin, a cheese factory. 28-foot depth tank. We had a flexi line here. We just dropped it into the water. As soon as that hits the water, it's a lot less cumbersome, and you just kind of maneuver it into place with some ropes. We can then buoy that to mark where the placement is for retrieval, or just tie it off with ropes. But then all you're seeing there is, it's just that flexi PVC hose, and we add an air pump to it, and you have mixing in situ right there. Talking about the ballast here. So this is a ballasted unit, steel plate. We'll just mount the unit right to it. And this is actually one of our smaller models. So that handle there is just to be able to carry that around. So in say like a lagoon application, you wanted to drop one of these down into the water, and then you went to go dredge it, you can move it around. Just operators take it out of the way and do what you got to do near there, and good to go. All right, so this is cheese factory up in Wisconsin. Yes, sir. Now this is an older unit, older installation. We don't do this anymore, but it's an interesting video to see here. So I don't know if I'll be able to restart the video, but with rotometers, that's you have both flow control, but you're also seeing your flow rate. There we go. So what you see here is that the rotometer is going to bounce. And what that's indicating is that a bubble is being released at the bottom of the tank. This tank was 30 feet deep, and we know when that bounces, a bubble is being released. So that allows us then to count the time it takes for the bubble to get to the surface. It turns out to be about 7 seconds. in 30 feet, it's about 4 feet per second. So that bubble's moving very, very quickly, that large bubble moving very quickly through the water until it hits the surface. And then you see that upwelling of water coming up. No, it's not. This is wastewater. This is activated sludge. So this is just their process for post-treatment. But in anoxic zone, they love it. We're actually installing another dosed unit there for flocculation. It's being installed this week, I think, right down to the side of this, where we're dosing in pass to take out the phosphorus, and then they're running that water then through a membrane. This installation, super simple. We had just the units here. They didn't build the doghouse out yet, but 2 5-horsepower blowers, really small, compact. They're nice. One was running duty, one standby. When you take the look at the VFD, I don't know if you can see it there, but 650 volts, and then 4 amps, roughly about 3.5 horsepower, is mixing that 250,000 gallons of water. So very efficient, and this is very deep water too. So we're little over 12 psi for that compression. In most applications, we're going to be at about 20 feet. So about that 8-9 psi. As far as data goes, this third-party data, I didn't take it, so I don't know how they collected this exactly. But you can see just over time, top, middle, bottom is going to be pretty darn close. This is a ballasted application, so we actually sent naked units just like this down to Encinitas, California. The plant then poured their own ballasted concrete, put some bolts in there, and put them into their tanks where they wanted them. So this was originally, the whole idea here was he was coarse bubble mixing this area. It was supposed to be sort of an anoxic zone, but he was getting too much air in there with there's too much oxygen in with that coarse bubble mixing. So we put these out. We didn't tell him where to put them. He put them where we wanted to. But this is just a video he sent us, and it's basically converting that zone into anoxic. Plan will be this year, early next year, he's going to fill up the rest of his basins with these. Out in California, turns out my uncle lives about 20 blocks away from this plant, so it's pretty convenient. Go see him. This is a pickle factory in Wisconsin. We didn't do any of the design of the header system here. Our scope was basically from the valves down in each of the tanks. So there's 6 tanks here, all identical, 12 feet diameter, 12 feet deep, and all those tanks back there, behind there, are filled with pickles. They bought this compressor off of eBay, and then this was designed by a firm in Wisconsin as far as the header goes, but it's just a single 2-inch header running off and then branch piping to each one of the units. So what I'm doing here is walking around. This was during commissioning, so all I did was open all the valves full on, and so we're running six different tanks, 1 air source, and basically no control whatsoever. I've asked them to put a VFD on there to slow this down a little bit because they're really over mixing. But what this was designed for and why this project was interesting, so very corrosive. It was a saltwater brine that they're doing they're evaporating all this pickle brine, so they're not sending it to the plant. And then this is the storage until they take it out to disposal, just keeping all that mixed. All the parts, all the wetted parts had to be non-corrosive. So we had, I'll go back here, slide. Oh. So you can see here on the top right here, PVC piping, fiberglass strut, there are nylon clamps on there, And then this unit was then mounted to a fiberglass slab, and then that was glassed into the floor. So these fiberglass tanks, completely non-corrosive and basically no maintenance whatsoever. This one was a loud one if you want to. Can I turn it down? Oh. Pardon how loud this is. This was commissioned last September. This is in Webster, New York. Also a this is a milk plant. And added the mixers. What's interesting about this is on commissioning, so it's clean water right now. But you can see these eddy currents that are forming. So when that bubble rises, it's upflowing all that water, and then it sends out radially from the bubble. When two bubbles collide, or when two the wakes collide, that's where you'll see downflow, and that's where you're going to see those eddies. So two bubbles collide, and that's the currents that are being formed in there. So this tank was another, I think this was 300,000 gallons, and then, yeah, 7.5 horsepower. So I think we're running at about 4.5 or something like that for 4 bubbles a minute. What you'll notice though, this is a very deep tank, and the bubble will start to break up after about, of this size, will start to break up after about 25 feet. So you start to see that, do that, but you're still upwelling quite a bit of water. And all that bubble's held together in the lower depths. So you're not getting a lot of oxygen transfer at all. And then once solids are in there and you up the viscosity a little bit, everything's held together even more. So this is an old slide. I like it because I spent a lot of time on it. But so essentially what we're saying here is there's a lot of different ways to feed air. You can have as many controls as you want, but the main idea is you fill them with air, they'll make bubbles. The rate at which you fill air determines the rate of the bubble release. So you can change the intensity of that mixing. So if G value is a concern and you wanted to do a gentle flocculation or something to slow everything down, you just decrease the flow rate of air. How that can be done on a plant system. So if you're using plant air, especially if you have common header pressure, very easy. It's just, variable control valve, variable orifice valve. If we're using a dedicated system, a dedicated blower, then we just have a VFD that can turn up and down. And then we can individually, so if running a couple different zones, we can adjust the rates with just some simple valving. You can use different air sources, throttle back and forth. It's designed to be really simple, but also really flexible in the application. Just talking about power consumption just a little bit, it's just the compression rate of air. So comparing to high pressure systems, just since we're not compressing to that high 100 and some PSI, and then dropping that back down to the pressure of the water, we simply need to break the head pressure. So where that diffuser is, it's basically an aeration grid, and then you fill it up with however much air. Say at like 20 feet of depth, the effective volume of this with the compressed air is about 2.4 CFM or SCFM, or standard cubic feet, per bubble per minute. So 2.4 SCFM will give you a bubble a minute in 20 feet of water. You go up to about 10 SCFM per unit for 4 bubbles a minute. The difference between a bubble every 15 seconds and a bubble every 20 seconds isn't all that much. So we'll generally spec to about 4 bubbles per minute, and then in operation we'll see that even brought down. So we're looking at about 7.5 SCFM per unit, which, as you can see, just the operational costs of this are quite low. Just a couple more videos here. This is a MBBR system where large bubbles are being used in conjunction with fine bubble aeration. So we get the generally in MBBR systems with the little spaghetti noodles, you're using coarse bubble aeration to do both the motive force and to aerate, which is somewhat efficient, but add the efficiency of fine bubble for getting the oxygen into the bulk fluid, but also then using the large bubble for mixing purposes. It's very, very effective. This plant was running very low carbon, so we're seeing some bulking there, but that's more on the operational side of things. This is a supplemental mixing application, so this is a landfill leachate. Unfortunately, the only video I have of this, but this is also MBBR media, but it's called Mutag. They're these little wafers. They kind of look like little tiny Pringles. Very, very light, and they don't become neutrally buoyant until biology is formed on them. So this whole tank was being mixed by a xylem big banana mixer, but you'd have all this rafting in here. So you're basically stirring the tank, wasn't doing a very effective mixing of that top layer. So you see this rafting, everything floating on the top. Like I said, this is the only video I have. This was right after they put this in. I was told that just a couple days later, all that rafting was gone and everything was mixed into the tank. So that was just one of these units with a concrete base, and then we just threw it over the side of the railing there. And then I think they bought a compressor from Harbor Freight just to run air to this for those bubbles. I'll play that video one more time now you know what's happening. So you can see all the swirling down there. I know the video's not great, but that's lifting up, basically moving everything out from the center and then really mixing it up in the middle. This is an application, this is a municipal plant up in Wisconsin as well. And this is clean water at this point, but this is running now. This is an Aquarius nebula system, so I'm not sure if you're familiar with those, but they're basically these cartridges with curtains of media on them, so they're fixed film, but it's like just a whole bunch of surface area hanging on the thing. Whole idea of here was to circulate water in between these cartridges and keep that zone anoxic. At the plant now, they've taken the air down to about 1 bubble a minute for all these units, so I think it might even be lower than that, but about 1 bubble a minute, so there's 3 units in there, about 7 SCFM or so. And that's all I have, but I'm happy to take any questions you might have right now. But we want to make your plant better with bubbles, I guess. So thanks a lot for your time.
If you guys, I'll pass around Charlie's cards too if you guys have questions later. I'll give my cards as well if you guys have any other questions. But I appreciate your guys' time. Thank you, Jason, GPSD, as always. Yeah, if you guys have questions, feel free to fire them off. We're pretty laid back, so keep it informal.